Okay, similar triangles. So let's just recall that if we've got two triangles that are similar, and similar was this little squiggly sign, then those triangles' sides are in ratio in accordance to their scale factor. So what that means is A to B compared to, and then the similar one on the other triangle is DE. And it actually doesn't matter which way we have, like we don't have to follow the scale factor. We can take the reciprocal of all of the ratios. They'll still be in ratio. It won't calculate the scale factor, but it will calculate the same ratio between all the sides. But you need to make sure that you are dealing with one triangle as your numerator and a different triangle as your denominator. So if you do that, then, okay, we've looked at AB, and if we take BC, then that would be equivalent to EF on the other triangle. And if you took the first one and the last one, which is AC, that would be equivalent to DF on the other triangle. And it turns out that this is always true. This similarity property is always true if there's something special about the three angles of these triangles. And what's that special property? Well, these two angles need to be the same. So the angle B to A to C, BAC, BA then C, and E then D then F. So the same ordering of the letters as we have to be exactly the same angles. And that has to be true not only for one angle, that has to be true for all three angles. That the angles that are in the corresponding places have to be exactly the same. And if they are, then the two triangles are similar. Now, sometimes it's not as obvious that the three angles are exactly the same. Let's take a look at an example where it's a little harder to see the angles are the same, but they are, and we can actually use that to help calculate some missing information. Okay, so here's this example where we've got a couple of triangles that are kind of overlaid, embedded. One triangle is embedded into the other, and I've got some information. So I've got a side length of 4, and across here is 6, and another kind of part of my side is 5, and I'm trying to figure out this bottom part, CE. I'll call it X. We'll give it a letter that we're actually trying to figure out. Now, I can't go and calculate these things unless I know that the sides are in ratio, and I can't know the sides are in ratio unless I know that they're similar triangles, and I won't know that they're similar triangles unless I can find three equal angles. So, and it's even hard to see where are the two triangles that we're working with. Well, one of them is this big triangle here. And so if I were to recopy that triangle out, and for some of you you'll need to do this. I certainly do when I'm working on it as well. So let's go and copy that triangle, and I'll just do that underneath. And that's got a side length between A and C of 9, and this down here is X. And let's just find another triangle in here. There's this top triangle here, and I'll copy that one down on the right-hand side. I've got some information. This one's 4 and this one's 6. Now it turns out these are congruent, not congruent, these are similar triangles. This angle at the bottom here is the same as this angle here. So this one, AEC, is the same as ADB, and the reason that it is because of these parallel lines. So in green there's those little arrows. That means that BD and CE are parallel, and so these two angles, angle 1 and angle 2 here, are equal because they are corresponding angles. Likewise, this angle right here and this angle here are also the same value because of the parallel lines. Those are also corresponding. And finally, I've got this angle at the top, and this angle at the top is the angle A, and that's this angle, and in the small triangle, that's this angle. And you can now see that you have three equal angles. And when it's true that you have an angle, another angle, and another angle, a shortcut is AAA that we use in mathematics. then these two triangles are similar. And so we can write a similarity statement, and we just have to be a little bit careful with it. So A to C to E, so this triangle ACE is similar to, and I just have to make sure I get it in the same order. So there's this top angle here and then the dot, top angle and then the dot. So that's A and B, and then the dot goes over to the shaded one, dot goes over to the shaded one, which is D, and then back up. Sometimes the similar triangles are rotated or out of a bit of an order, so you have to be careful, very careful with setting this up. Now that I have this, I know that my sides are in ratio, so I know that from A to C is the same as comparing AC compared to AB, is the same as comparing CE to BD, and that's the same as A compared to E and A compared to D. So again, I've got the triangle ACE on the top, and I've got all of the parts of triangle ABD on the bottom, and now I can start filling some information in. So I can take this and I can say, well, A to C is 9, and on the other one, A to B is 4, and C to E is what I want to try and figure out, and B to D is 6. I really don't need to do anything else. I was never asked how big AE is. I don't know how big AD is. It actually doesn't matter. All I need to do now is take this and go and solve it. And the way of solving it is multiply both sides by 6. 6 cancels. 6 times 9 is 54. 54 divided by 4, which is 54 over 4. 54 can divide by, not 5, 54 divides by 4. That would be 27 divided by 2, which you can certainly leave it as that, or 13.5. And so that missing side across the bottom is 13.5. Sometimes when these triangles are embedded like this, it can be a little bit difficult, so I encourage you to go through all of these steps. Draw out the separate triangles, make sure you know where your AAAs are, set up your triangle congruency or triangle similarity statement, put down all the sides that are in ratio, and then start to plug things in. It does get a little bit tough to do this without going through those steps. Okay, we'll see you in class.